Hello everyone, welcome to Rasayan Academy guys. So this is another topic discussion video for all of you and it continues in the series of stereochemistry. Now I have already uploaded a lot of videos for stereochemistry for you to see and learn from there and to be able to directly solve CSIR NET and GATE questions. This is another small topic which is really scoring and you must not miss this out. Enantiomeric axis and optical rotation. Alright. So yeah, before moving onwards, let me quickly remind you to like, share and subscribe to the channel if you already haven't to Rasayan Academy, and more videos like these are going to come up for to help you guys. So, first thing, guys, I hope that you have a little idea about the topic optical rotation. Okay, what is that? Optical rotation is very simple. When you are passing a monochromatic plane polarized light, all right, when you are passing a plane polarized light, which is actually just going to vibrate or sorry, just going to move in one plane. Let's say this is your plane polarized light and monochromatic as well, having a single wavelength. So when it is passed through an organic sample or any molecule which has to be optically active molecule, so that active molecule is going to interact with the plane polarized light and it is going to rotate the light either to the right hand side. Now this was your original position, this has moved clockwise, this is your rotation to the right, or it can rotate it to the left as well. So the ones who rotate the light to the right are called dextrorotatory and the one which rotate to the left are called levorotatory. All right, so these are your optically active molecules. Now how do we measure the optical activity? That is what we are going to talk about. And what about the solution? Is the solution 100% pure, or it is having, let's say, some excess of one of the enantiomers? That is what we are going to talk about. So an optically active molecule is chiral, it has enantiomers, and that is what we are going to talk about. How much is the concentration of the enantiomer in that particular solution we are measuring the optical activity for. Okay, so let's start about the term specific rotation. Now, what is the difference between the optical rotation and specific rotation? So, as you get from the name itself, specific rotation means that it is going to be specific to a particular compound on a specific wavelength. So, the wavelength has to be mentioned on that particular temperature and that particular wavelength. It is always going to be the same. All right. So yes, it is also represented as the specific rotation, that is alpha, lambda constant and temperature constant. It's mentioned like this, specific rotation. Okay. And your optical rotation is just mentioned like this, alpha. Alright, so this is your optical rotation, simple. So there must be some formula correlating the optical rotation and specific rotation. Here it is very simple. Optical rotation is what you observe in the degrees. So in the polarimeter, you observe the angle of rotation. That is called your optical rotation in degrees. Now, from this angle, taking the length of the solution in decimeter, always take the length of the solution in decimeter only. That is your length of the polarimeter tube. Taking C as the concentration of the solution in gram per ml, right? So, this is what you have. Now, taking both of these variables, you divide the observed rotation by length and concentration, you get the specific rotation. All right. So don't forget to convert the units into decimeter for the length and gram per milliliter for the concentration. All right. This is super important. This is your overall formula. Okay, we are going to use this many times. Now, let's do a question on this. Calculate the specific rotation of 1 molar solution of 2-chloropentane in a 10 centimeter cell when the observed rotation is plus 3.64 degrees. Alright, so what is being asked? Specific rotation is being asked. Concentration is given to be 1 molar, but we don't want this unit. We have to change it. Length is 10 centimeter. We have to change this as well. Observed rotation is plus 3.64. What do you mean by plus and minus? Once again, when the plane of plane polarized light is rotated clockwise, it will be plus or small d. When it is rotated anti-clockwise, it will be L or minus, like this. Okay? So we move onwards. This is your dextrorotatory sample. Alright, and we calculate the specific rotation. Now, first thing, you have to convert the concentration molar to gram per ml. This is super important, guys. How are you going to do that? So 2-chloropentane is given. You can easily find out the mass of 2-chloropentane. So the mass of 2-chloropentane is 106.5 grams per molar. That is your moles per liter. That is per 1000 ml. So this is going to be per 1000 ml. All right. What do you mean by 1 molar? That is 1 mole per 1000 ml. Absolutely. So 1 mole is equals to, when it is 1 mole, it is going to be molecular mass is going to be equals to the molecular weight. All right. So yes, your weight and mass, both of these are equal. That is why you can just directly put it over here, and from this you get the formula 0.1065 gram per ml. All right. So now if you want to calculate the specific rotation, that's going to be really, really simple. Just put it into the formula alpha divide by L into C. Now concentration you have changed to gram per ml. Now the length also you can change. 10 centimeter is equals to 1 decimeter. Please remember this, because 1 liter is 1 decimeter cube, and that is why it is 1000 cc. Just remember this. All right. So yes, now the alpha value that you have got is plus 3.64 degrees divided by length, which is 1 decimeter, multiplied by your C value, concentration value, which is 0.1065 gram per ml, right? So what is the overall unit of the specific rotation? As you can see, this is the optical rotation will be in degree. So this is degree decimeter inverse ml per gram inverse. This is going to be your overall unit for the specific rotation. All right, and it's it's not necessary for you to remember the unit, because you can directly find this out. It's not very difficult. Okay, so the answer comes out to be 34.178. Yes, this is your correct answer. 3.64 divided by 0.1065. Yes. So this is your correct answer for this particular solution. Now guys, we are going to move onwards, and we will see plenty of more useful formulas. So first thing, let's find out the optical purity. So optical purity, what is that? Now this is a new term, optical purity, which means, let's say I have one solution. All right, I have one solution. This is 50% of, let's say, dextrorotatory sample plus 50% of levorotatory sample. If this is the combination, right, this is the solution having both of the dextrorotatory and levorotatory in equal amounts, then what will be the optical rotation that you check? The alpha, the observed value, is going to come out 0. Why? Because one half of the solution rotates it into the right direction, the other half rotates into left, and when both of these are equal, the optical rotation will be 0 and the specific rotation will also be 0. Alright, but let's say I have taken 75% of D and I have taken 25% of L. Okay, then what is going to be the alpha value? What is going to be the specific rotation? What is the optical purity of the sample or the enantiomeric excess of the sample? That is what we have to find out. Okay, so just by looking at the percentages, I can say that D is there in excess. D is the enantiomer which is present in excess. Now, how much is the excess? That is called the enantiomeric excess. Okay, how much excess? That is the enantiomeric excess. So we will just do 75 of D minus 25%. We will say 50% enantiomeric excess. Alright, so this combination gives you 50% enantiomeric excess of the dextrorotatory isomer. Alright, so it doesn't mean that you have 50% of the D isomer over here. No, it means it is excess. Alright, now how do you go back from here? Let's say to a question it is given 50% enantiomeric excess of D, the dextrorotatory sample. It is given like this, and the question is asking you find out what is the percentage of D and L. So what you do is, from this you understand that 50, if 50% is the enantiomeric excess, which means the situation is D minus L is equals to 50%. This is the situation. Yes, isn't it? Because the D1 is excess. Now you already know that in the solution, if I say I have a criteria of 100%, in the solution, who is making the 100% optical activity? Both the D, L, N, right? So the D and L total will make 100% of the sample, and D minus L will make 50% of the sample. So this equation is going to help you out to get the percentages. So this is 75% of D. From the same equation, D minus L equals to 50, you can also find out that L is going to be 25%. So this is how you go backwards. This is how you go backwards from the enantiomeric excess value. All right, I hope that you this made sense to all of you. When this kind of a condition is given, you find out the excess. This one is the in the excess, and when it is mentioned 50% of enantiomeric excess of D, you mean the actual percentage of D is 75 and the actual percentage of L is 25%. Okay, so now we look at the equations. Optical purity, I hope you have understood. Now, what is the difference between the optical purity and enantiomeric excess? It's nothing that optical purity is mentioned in decimal form. Enantiomeric excess is used in the percentage form. Just the same thing. Alright. So optical purity multiplied by 100% is your enantiomeric excess. Just note these formulas down somewhere. Okay, so optical purity is equals to, there's one more important formula. How can you find this out? Specific rotation of enantiomeric mixture divide by specific rotation of the pure enantiomer. Always, always remember this. The alpha specific, all right, we are talking about the specific rotation. All right, specific rotation of the mixture and specific rotation of the pure enantiomer. Now, which pure enantiomer? It could be D also, it could be L also. We just have to cancel the sign. We will see this while solving numericals. Okay, so ये देखो, for example, if the specific rotation of an enantiomeric mixture is plus 25, all right, the specific rotation of an enantiomeric mixture is given to be plus 25 degrees, and that of pure enantiomer is plus 50. So you're just going to write plus 50 degrees over here. Then what is the optical purity? It is going to be 0.5. This is your decimal value. And what is the enantiomeric excess? It is 50% coming from here. Okay, so This is your enantiomeric excess. And now if I ask you to find the RNS percentage, you will very gladly say that one of your enantiomer, which is there in the plus form, right, that is there in the excess. So your plus enantiomer is 75% and your minus enantiomer is 25%. Just now we had found out. Absolutely very simple. So it means the mixture is 50% optically pure. What does this mean now? Just a different way of saying the same thing. When I said enantiomeric excess is 50%, which means that in your sample, you are having 50% of enantiomeric excess of the positive isomer, let's say. That means the other one is there in the racemic mixture, which means that 50% of racemic mixture is present. How can I say that? 50% of enantiomeric excess, matlab this 50% is pure positive isomer. The remaining 50% of the sample is racemic mix, which means I can say the remaining 50% is 25% of positive and 25% of negative enantiomer. That is why when you add the total positive, you get 75%, which is right over here. And when you take the negative, you get only 25%. Alright. So that is how I can say that this 50% is optically pure and the other 50% is a racemic mixture. Okay. So that is just another way of saying optical purity 50% and optical purity of the remaining part. It's a racemic mixture over here. All right. Now, also, I have made you understand that optical purity of a racemic mixture is going to be 0 because there you will have 50% of the D enantiomer and 50% of the L enantiomer. So that is why the optical rotation is going to cancel out. So the optical purity will also be 0 and enantiomeric excess everything is 0. Alright. So optical purity of a racemic mixture is 0. Now the same things guys for the enantiomeric excess, it is calculated as percentage optical purity. I just told you optical purity into 100%, that gives you enantiomeric excess. Alright. And there is one more formula. Let's say a question is telling you that you have your R enantiomer as 75% and you have your S enantiomer as 25%. What is the enantiomeric excess in percentages? So you can just directly find out here 75% minus 25%, that is 50%. So this was too easy. But let's say I am giving you the values in grams. Let's say I have told you 7 is there in 10 grams and the S is there in 5 grams. Now you find out the enantiomeric excess. How are you going to do it? Very simple. You are going to use this formula over here. Enantiomeric excess is equals to 10 gram minus 5 gram divided by the total 10 plus 5, 15 grams into 100%. This is how you find it. Alright, 5 divided by 15 into 100%. Okay, so this is how you guys do it, guys. This is 3 and this is going to give you 33.33%. Alright, so this is how you calculate the enantiomeric excess when the gram is given, when the mass is given like this. Okay, not the percentage. Alright, so let's now apply all of these formulas on some CSIR NET questions. Now they are not so direct because here the unitary method and concept has been used. So first question I have taken from December 2011. An optically active compound enriched with the R enantiomer 60% enantiomeric excess exhibited the specific rotation of 90 degree. Now first understand this question, this first sentence. What is it telling you? There is an optically active compound, but it is enriched only with the R enantiomer being 60% enantiomeric excess. So 60% enantiomeric excess of R isomer will show you a specific rotation of plus 90 degrees. All right, and guys, please understand it is not necessary that always the R will show plus. The R in enantiomer can show minus also. That is experimental. Okay, you cannot just predict that. Yes. So there are two parts of this question. 60% of enantiomeric excess of R shows this much optical specific rotation. तो 100% कितना show करेगा? 100% enantiomeric excess will show how much specific rotation that can be done by the unitary method, isn't it? Into 100%. Yes. So how much is this going to be? This is 150. 150 degrees of your pure enantiomer. Now, when I'm saying 100% enantiomeric excess, that means there is only one isomer, isn't it? Only one isomer, 100% pure. I am talking about the R enantiomer. So this is basically the specific rotation of a pure R enantiomer, isn't it? So the first condition, the first sentence is given to find out, it's only given to find out the pure R isomer. You know, sometimes it is mentioned that your pure R enantiomer is going to show you plus 150-degree rotation. Sometimes it is not mentioned so directly. So that is what you find out from this sentence. Okay. Now, the second is if the alpha D value of the sample is minus 135. Okay, wait a second. You might be confused that if 60% enantiomeric excess है तो यहाँ minus कैसे आया? It's not possible because when it is mentioned that the sample specific rotation is given in minus 135 degrees, which means which isomer is excess? S enantiomer is present in excess because the R has got positive, which means the S has got minus. So this is your sample, which is basically your alpha mix. Alright, it is the specific rotation of the mixture. Now you have to find the ratio of R and S enantiomer would be. Now, before finding out the ratio, you have to find out the percentages of R and S enantiomer. How do you do that? So, the pure R enantiomer shows you plus 50, which means that the pure S enantiomer is going to show you alpha D of the pure S enantiomer is minus 150, isn't it? Yes. So, how do you find out in the sample? How do you find out the specific rotation of the S enantiomer minus 150 is minus 150 degrees. All right. So how do you find out the enantiomeric excess or optical purity? Okay, we have just used this formula over here. Specific rotation of enantiomeric mixture divided by specific rotation of pure enantiomer. All right. So optical purity is going to be equal to specific rotation of the mixture divide by that of the pure enantiomer. Here I have taken pure enantiomer to be S because I want to cancel out the minus signs of both of these. Okay, that is why. So this is going to be 0.9. The enantiomeric excess is going to be 90%. Alright, and then how do I find the R and the S enantiomer? You know already that S plus R is equals to 100% and R minus S, R, or let's say like right R difference S over here because the S is there in excess, right? So from here you are going to find out that the S enantiomer and the R enantiomer percentages are like this. So R is there in 5%, S is there going to be 95%. Okay, now you see that S is 90% excess from R because this is your enantiomeric excess. Alright, now if you find out the ratio of R and S, that's simply going to be 5 is to 95, which is 1 is to 19. Alright, so your answer becomes option number A. R is 2, S is 1 is to 19. So what did you do in this question, guys? Please understand it's a super important topic. The first sentence only gave you how much the pure R enantiomer is going to be. Okay, so pure R enantiomer is going to be plus 150. If you have found out pure R, you can directly say what is pure S. Pure S is going to be minus 150. Alright, now you use this information, pure S is minus 150, with this value to get the enantiomeric excess over here, because the formula is minus 135 divided by minus 150, that will be multiplied by 100 to give you enantiomeric excess. Okay, then from the enantiomeric excess you have found out the RNS percentages, and then your RNS ratio. So this is a simple question which has been asked in December 2011. Let's move onwards. So December 2012 question. The alpha D of a 90% optically pure 2-aryl propanoic acid solution is plus 135. So see, this is giving you the same information once again. It is not directly telling you that your optically pure solution is this much. It is saying 90% optically pure. So what you have to do is to find out the optical rotation of any one isomer, you have to do unitary method. Okay, so let's say you have done unitary method. Dextrorotatory sample is let's say कि 100% कितना होगा, pure dextrorotatory isomer will have the specific rotation of plus 135 degrees divided by 90 into 100%. All right, so this is what you find out, and this is going to be 150 degrees once again. All right, so this is your 100% optically pure isomer giving you 150 degree plus 150 degree. Okay, this is the information you got from the first sentence. On treatment with a base at room temperature for 1 hour, all right, you are treating the D isomer with a base. The specific rotation changes to plus 120 degree. What does that mean? That in the beginning of 1 hour, you had the alpha D, which was 100% D isomer. This was 150 degree. Now, when you are doing 1 hour of reaction, it becomes plus 120 degree, which means that some of the D isomer has also converted into L, and that is why it is cancelling out. So we have to find out ki how much has converted to the L isomer. That we can do easily by the enantiomeric excess. So on treating with the base after 1 hour, it is 120 degrees. Let's find out the optical purity. So that will be alpha mix divided by alpha pure. All right, that is going to be 120 divided by 150 into 100%. Okay, so when we are applying 100%, we directly take the enantiomeric excess. All right, optical purity is a decimal, enantiomeric excess is percentage. So let's directly take the percentage. This is 80% pure now. This is 80% pure having the positive enantiomer excess. Okay. Now, all right, this is sorted. The optical purity is reduced to 40 degrees, 40% after 3 hours. Now, guys, there is a difference between reduced to and reduced by. Reduced by means you have to minus by 40%, and reduced to is just directly take the 40%. Okay. Now, after 3 hours, this was the case after 1 hour. Okay. After 1 hour, after 3 hour, what is happening? After 3 hour, the optical purity or the enantiomeric excess has reduced to 40%. Alright, if so, the optical purity of the solution after 1 hour, which we have already found out 80%, and the specific rotation after 3 hours respectively would be. So what is the formula of optical purity or enantiomeric excess in percentages? Let's take the enantiomeric excess. The formula is alpha mix divided by alpha pure, and here you have 40%. So you have to find out alpha D after 3 hours. You have to find out the alpha mix over here. So the specific rotation of the mixture after 3 hours will be 40 divided by 100 into alpha pure is, we have just found out, 150 degrees. Okay, so this is going to come out 60 degree over here. So your answer is supposed to be 80% and 60 degree. This is your answer. So don't be confused in these kind of question. The first part of the question is only giving you the information about a pure D enantiomer, which is plus 150 degree. The second part of the question is telling you that now you have changed the enantiomeric, the optical purity, which means alpha mix has changed. So that is why you have to find the optical purity of the solution after 1 hour, that is 80% pure, by using the simple formula. Similarly, by using the same formula, here you just have to find another variable, that is your alpha mix, nothing else, same formula being used. Okay. June 2014 question. An aqueous solution of an optically pure compound of concentration 100 milligram in 1 ml of water measured in a quartz tube of 5 centimeter length was found to be minus 3 degrees. The specific rotation is. So which formula you are going to apply over here, guys? Just think by yourself. It is very simple. Yes, the most basic formula over here, that is your specific rotation has to be found out. This is alpha divided by L into C. So what is the L value? It is 5 centimeter, which means it is 0.5 decimeter, isn't it? You have to convert to decimeter. Don't forget that. All right. Then 100 milligram in 1 milliliter. So you require gram per ml. So this is going to be how much? Grams? 0.1 gram. Alright, so 0.1 gram per ml. This is the concentration. Alright, so your value has to be minus 3 degree divided by 0.5, that is your decimeter, multiplied by 0.1 gram per ml. So this is coming out to be minus 3 into 100 divided by 5. So minus 60 degrees. All right, so the answer is going to be minus 60 degree, and we have used a very simple direct formula over here. Just take care of the units. Okay, nothing else. Answer is minus 60 degrees. Moving onward, next question, very nice. June 2017 CSIR NET paper. The question is asking you the specific rotation alpha D for the S plus 2-butanol. See, here the S is plus, so you cannot say S is minus, right? Not theoretical. So, specific rotation alpha D for the S plus 2-butanol is 10 degrees milliliter per gram decimeter. Right, now you confirm this is specific rotation by such a big unit. The observed optical rotation of a sample. See, this is observed optical rotation. What does that mean? It is not specific, it's only alpha. And this is alpha D which is given. So alright, you must have to convert one of them. So you should convert this into alpha D. Okay, specific. Let's see. Now the observed optical rotation alpha observed of a sample composed of a mixture of R and S 2-butanol is minus 0.45 degrees. So when you say that your alpha pure S is plus 10 degrees, and when you say the alpha mix is minus, not the alpha mix, it is simple alpha, right? Not the optical rotation specific one, minus 0.45. So by the change of sign, what can you say? Who is there in excess? So you say that definitely the other isomer is there in excess. So if pure S is plus 10, the pure R is going to be minus 10, and the R enantiomer is there in excess. How do we know? We know by the sign. All right. Yes. So we are going to convert the alpha mix into alpha pure mix specific rotation. That is the first thing that you do. And see, the value is also given. Cell path length is 0.6 decimeter. Very well. 0.45 degrees divide by, already in decimeter, 0.6 decimeter, multiplied by concentration is already gram per ml. How good is that? You don't have to convert. Gram per ml. Alright, and this was your milliliter upon gram decimeter. Now, this is all going to cut out, and the value that you get is alright, this is going to be minus 5 degrees. Alright, so now you can compare. Now you can compare key, because all of these are into specific terms. Pure specific, and this is also mixture specific. Okay? The percentages of R and S enantiomer in the sample are, how do you find out? Very simple, just find out the enantiomeric excess, that is your alpha mix upon the alpha pure into 100%. So now when the alpha mix is there in the minus 5 degrees, you have to take the negative enantiomer only, this one, because you need to cancel out the signs. You take the pure isomer, which is the R, you take minus 10 degree into 100%. So how much is this going to be? 50%. Alright, so the enantiomeric excess is 50%. What do we mean by that? So when the enantiomeric excess is 50%, that means it is R minus S 50%, isn't it? And the R plus S, that is going to be 100%. Alright, by these two equations, you can say that 2R is equals to 150, and the R is going to be 75%, and the remaining S is going to be 25%. We have just done it. There are two ways of doing it, whichever you want, whichever you think is easy for you, you can just try that out. So the answer is option number D over here. Okay, so guys, we have done 4 important questions from CSIR NET examination, and you know that how these questions are being put. So you can now solve further questions, further PYQs by yourself. And if you think that the video is helping you, then please share it with your friends. Also, subscribe to Rasayan Academy if you already haven't. Okay, and guys, like to banta hi hai, so please like it as well. I'll see you all in another video.